Hello and welcome. So last time we looked at the support vector machine with maximum margin classifier, and we saw that with good linearly separable data, we are able to get the hyperplane with the maximum margin, right? And last time what we saw was the hard margin SVM, right? And we saw the problem formulation, and we got this quadratic linear programming, right? And we saw that our objective function was the norm of our W vector and under this constraint, right? So this is what the hard margin SVM. So in hard margin SVM, we do not allow any kind of misclassification. You will always get a hyperplane without any misclassification. So all of your data will classified correctly with the hard margin SVM, right? So today what we are going to look is at the soft margin SVM, and in soft margin SVM we will see that we will allow some misclassification, and why we are doing that. So you will see that why we are doing that, the reason behind it. So we would allow some misclassification to get some benefit, right? So if you see, if data is completely linearly separable, then with the hard margin SVM you can have the solution that with this hyperplane, right, that will have the maximum margin, right? And let's suppose that what if you have data and you have some outliner here, right? So this one of the data is here, or let's suppose make it here. So now if you run the SVM, then so what hyperplane you will get is this, right? So you will get this hyperplane maybe, right? And with under this constraint, this, right? So under this constraint, this, that means all of your data have classified correctly, right? And and this is the margin you are going to get from your hyperplane, right? So you see that due to this outliner, there is significant change in your hyperplane, right? Due to this only one outliner, there is significant change in your hyperplane, right? So and now if you come up with some test data, and if your data belongs to here, so this is going to be classified as the 0, right? Because this is at this side, right? But maybe it should belong to this cross, because this is very near to this cross. And why it has happened? Due to this only outliner, right? So in this situation, what we should do, we should allow some misclassification. We should not worry about this outliner, and we can ignore this outliner, and if we ignore this outliner, then we will have the hyperplane, separating hyperplane, and with the maximum margin will maybe so I am ignoring this outliner, right? So in this case we will have the hyperplane that will look like this, and with the maximum margin, right? So this is what we call the soft margin classifier, where we allow some misclassification, right? And okay, so it may happen that we could have the outliner in your data set, and due to this only one outliner, our complete hyperplane have got shifted, and so it's good that if we allow some misclassification for some few example, or maybe few outliners. So it's a good for the it's a good if we consider that case also, right? So we can do the misclassification. So so this was our constraint, right? So what modification we can do? So let's suppose that we allow some misclassification, and so within the constraint what we can do is we can introduce this variable, and we are subtracting it from this -1, right? And this variable what we call is the slack variable, right? So what we are doing is that we are adjusting our width, right? Width of the street, right? With this variable, that what we are calling is the slack variable. So if this is the hyperplane, and if this is the width, and this width is in both sides, it is equal, right? So with this chi, we are shifting few, maybe up or down, maybe here or maybe here, right? So we are introducing this slack variable in our constraint, right? And it will have effect on our objective function also, right? If we are doing some changes in our constraint, then obviously we will have to pay the cost in the objective, right? So slack variable, that is chi, allow some constraint violation, right? Creating more flexible hyperplane, right? So we will have the flexibility that maybe we can with this slack variable we can shift our hyperplane from this green line to this, right? And why we will be able to shift? Because we will be neglecting this outliner, right? So that is what the flexibility we want, right? Okay, so after introducing this slack variable in our constraint, so obviously that we will have to pay the cost for it in our objective function, right? So this is what the addition we have made in our objective function, right? So this is the cost of the slack to objective function, and this C is the cost, right? And this slack variable is for all of your data point, right, from I to n. It depends, like for which example. Here for this example we need to have some, right, and not for the all example, right? So now our objective function will be changed to this, right? So now our objective function will be minimize this norm of W plus this, right? And with the constraint this, right? So this is what we call the support vector machine with soft constraint, right? And if you have already gone through, then what's the objective of this norm of W? What we minimize? So minimize is model complexity for better generalization. And what this term is going to do is it's going to penalize constraint violation for accurate classification. So I will describe this term more, right? So let me first tell you about this C, right? So C controls the strictness and flexibility, right? So if we have this large C, if the value of C is the large C, what we want to achieve is we want to achieve the minimum, right? If we have the large value of C, then our more if we are minimizing, then our more focus would be on this term, right? If we have the large value of C, right? Because we want to, so if we have large value of C, then prioritize strict classification. So this is what term is going to be prioritized, and it will potentially lead to the overfitting. So let me explain you that if we have the large value of C, then we will try to keep this as minimum as possible. And if the slack variable is minimum, and what could be minimum? It could be 0, right? So slack variable is greater than equals to 0. So the minimum could be 0, right? So we are not introducing any slack variable. If C is large, our objective is to minimize. Then what we will try to do, we will keep this term minimum to make the overall objective function minimum, right? So in this case, what will happen that, right, and if C is small, then we will have some flexibility on choosing this slack variable, right? If C is small, right, then our more focus on be to minimize this, right? And we could have some Xi with some little value, right? So if C is small, then we could have Xi some amount, right? So and our more focus would be on this to minimize, right? And if C is large, then it will potentially lead to the overfitting, right? And if C is small, then we will be potentially lead to underfit. So if C is small, then what I said, that if C is small, then our main focus would be to minimize this. And since C is already small, then what we can do, we can add some slack variable, right? We could have some value with the slack variable, right? So if C is small, so we allow slack, right? So we are allowing some value to slack, and it will potentially lead to underfit, right? And if C is large, then in this case we are not allowing any slack variable. That means if SVM is running, then it will completely classify your data, strictly classify your data, right? I hope it makes sense to you. And so if it is completely classifying your data, that means it is overfitting. Overfitting means it will have the high bias. And if you are introducing with some slack variable, then so in this case we will underfit, and that will lead to the high variance, right? So okay, so same problem. So this was the linear programming, so quadratic linear programming. Now we can have the same problem with some other that we can call the unconstrained formulation. So in that problem we will not have any kind of constraint. So how we can modify our problem? So what we can do is, you see this one, right? This. So what we can do is Xi will be 0 if data is classified correctly, right? And there would be some Xi if, and what would it would be that this amount, right? Because if you take Xi from here, this is what you are going to get. And in this case, so if Xi would be some quantity, if if we have this constraint, right? And Xi would be 0 if we have this constraint. This constraint means all the data has been classified correctly. And here this constraint means there will be some data that may get misclassified, and for that we will have some value for that Xi, right? And so we can write this to closed form, equivalent closed form. So Xi would be max of this comma 0, right? So 1 minus yi double transpose xi plus b comma 0. So we have this value of Xi that we can put in our objective function. So this was your objective function. Here we can put the value of Xi, right? So this is the value of Xi. We can put it here, right? So you see that now our problem has turned into this, right, in closed form, and we do not have here any constraint. So this term, what we call, is the hinge loss, right? And this term is the regularization, right? So this formulation allows us to optimize the SVM parameter W and P through gradient descent. So this is the form that you have already seen in the logistic regression, where this term that we are calling the hinge loss, there it was the logistic loss, log loss, right? So we can run the gradient descent on this problem, and we can have the parameter of value of W and P, right? Okay, now let's look at that large value of C and small value of C, right? So if you see that if you have the value that is C is equals to 100, right? So if you have C large, then what it is going to do, so C is large, that means that your slack variable will be close to 0. That means we are not introducing any slack, right? And if we are not introducing any slack, that means every data is going to be classified by SVM. So that is what you see, that even if this is the outliner, that it is getting classified correctly, right? So that is what is happening here. Now let's take maybe C is equal to 1. If you take C is equal to 1, then that means So C value is kind of less, we can say. That means Chi would have some value, right? Some small value, we can say. So that means we are allowing some misclassification. So we are not worrying about this outliner, and we are going to get this hyperplane, right, with this margin. Let's see. So you see that this is the overfit, and this what we call is the underfit, right? And if we take the C value very less, then this is what going to happen. So you can look at this. Okay, that was all about the soft margin classifier. Thank you.